Welcome back. In a previous video, we used determinants to find the inverse of a matrix. Now we're going to use the inverse to we're going to use determinants to find the area of a parallelogram. Since we do not include finding a determinant of a 3 by 3 matrix, although we could do that with our calculator, we're not going to do volume because volume is 3 dimensions, but area is 2 dimensions. If A is a 2 by 2 matrix, we can use the determinant to find the area of a parallelogram. So in our notes here, we say the area of a rectangle or area of any parallelogram is going to be the determinant of the matrix. Well, let's take a look at example 8. We're asked to calculate the area of the parallelogram determined by the points negative 5, 4, negative 1, 4, negative 3, negative 2, and 1, negative 2. I'm going to go ahead and label those points A, B, C, and D, and I'm going to label them in a clockwise order. So negative 5, 4 would be A, negative 1, 4 would be B, negative 3, negative 2 is D. Be careful with that. And 1, negative 2 is C. Now we're asked to translate the parallelogram so that the origin is a vertex. So we've got some options here. I definitely need to raise this up 2 units and shift 1 unit to the left. Really, that would take C and make the origin. So my translation here for my ordered pairs, if you will, we're going to do x minus 1. We're going to subtract 1 from every x value. That would give us to 0. And we're going to take every y value and we're going to add 2 to it. So that would shift point C to the origin, but then it will also shift all those other vertices by the same amount. Labeling, then, point A would become negative 6, 6. Point B would become negative 3, 6. Point C, and I'm going out of order because I'm going to move this guy here. C is going to move to our origin, isn't it? Excellent. That's going to become 0, 0. It's exactly what we wanted. And point D now will become negative 4, 0. So we've translated the parallelogram so that the origin is at the vertex. Well, our new parallelogram here is sketched out in red. In B, it says create matrix A from the vertices that are adjacent to the origin. So adjacent means next to. So we're going to use vertices B and D. Okay, vertex A is across from the origin, so we're going to use our B prime and our D prime vertices. So these are really A prime, B prime, C prime, and D prime. So we're going to use D prime and B prime. And we're going to translate those. So our ordered pairs, name the translated image using matrix A of vertex 1 and vertex 2, x1, y1, and x2, y2 from our points B prime and D prime. So matrix A will become negative 3, 6, our x1, y1, and negative 4, 0. In C, it says find the determinant of A. We multiply negative 3 times 0. We subtract negative 4 times 6, and we get 0 plus 24, and our answer is 24 units squared is the area of that parallelogram. In example 9, it says suppose you create a matrix V1, V2, so instead of writing our ordered pairs horizontally, we're actually going to write them vertically. So this means we have x1, y1, and then x2, y2. So our ordered pairs are written vertically instead of horizontally. It's a little counterintuitive. We'll create a new matrix A, maybe we'll just call it A prime, and we'll write our ordered pairs, and we'll calculate our determinant and see what we get. So when writing our ordered pairs, -3, 6, and -4, 0. Calculate my determinant. So I have -3 times 0 minus 6 times -4. And sure enough, I get the exact same thing. I get 0 plus 24. I get 24 units squared. So the lesson here, we can set up our ordered pairs vertically, or we can set them up horizontally, and we will still get the same area for that parallelogram. So we'll get some more practice with using determinants and finding the area of parallelograms when I see you in class.